Here we have a football combine, and we have a player who's going to do a 40-meter dash. We want to analyze that race and measure his explosiveness and top speed. In this case, explosiveness is a way to measure the ability to accelerate. We can also imagine that if this player is exerting himself, that the acceleration would be essentially constant because he would be pushing himself to achieve his maximum possible acceleration, which we could think of would be a fixed value. The top speed is another thing that we're interested in. This would be V final, the speed at the end of the acceleration. And so we're told that this player starts from rest, like he's doing a sprint, and he reaches the full speed in 1.7 seconds, at which point he's on the 13th hash mark. Then he holds that top speed through the end of the race, and we're asked what is the acceleration, the maximum speed, and his 40 time. That is the time it takes to complete the entire 40-meter dash. And finally, we will find position, velocity, and acceleration graphs for this motion. So the first thing we'll do is to draw a picture to represent the motion of this player. We're running in a dash, so we're running along a straight line. So we'll start with a horizontal coordinate system. Our player starts at the beginning in a racer's crouch, and if he is starting from rest, that tells us that the initial velocity is going to be 0. We're told that he starts running, and it takes 1.7 seconds to reach full speed, which is at the 13-meter hash mark. So when our runner is right around here at the 13-meter mark, we know that 1.7 seconds have elapsed. We also know that his displacement in that interval is 13 meters if he's gone from the 0 mark to the 13-meter mark. We don't know how fast he's going. We know that he has been giving himself the maximum velocity, the maximum acceleration that he is capable of over this interval. He hits his maximum speed here with some acceleration. We're going to assume a constant acceleration here. And then we're told that he maintains this speed. So if he maintains the speed, that means that we have uniform motion or constant speed during the rest of the race here, which means that he would finish out the rest of the race at that same speed that he had at the beginning of this interval here of uniform motion. We can see here, we'll need to know this later, that if he's gone 13 meters here and the total race is 40 meters, then his displacement here has got to be 27 meters. We don't yet know the amount of time that it will take for him to cover this distance. That's something that presumably we'll have to find. But we're asked about the player's initial acceleration. We've made an argument why we could imagine that acceleration would be constant or approximately constant. And so if we're trying to find the initial acceleration, we would use our constant acceleration equations. If we're going to use those, we'll start by writing out our constant acceleration variables. We know that the initial velocity is 0 because he's starting from rest, we're told. We know that the displacement over this interval is 13 meters. And we're told that it takes 1.7 seconds for him to cover that distance. So we have 3 pieces of information here. We're asked to find the acceleration at the very beginning. And so we can use our constant acceleration equations to find the acceleration. Take a moment to click pause and think about what equation you would use to find acceleration given this information. We can use this equation here that doesn't have the final velocity. We can plug in the values that we know and solve for the acceleration, and we find that the acceleration comes out to be very close to 9 meters per second squared. If we round that to sig figs, that would be 9.0 meters per second squared. So we found the initial velocity, the initial acceleration during this first portion of the race. We also want to find the maximum speed. We imagine that he speeds up to hit his maximum speed here, and he maintains that constant maximum speed for the rest of the race, which is why we're modeling that as uniform motion or constant speed. So this maximum speed here would be the final speed at the end of the acceleration interval, and that would be the speed we'd maintain during the rest of the race. So the maximum speed here would be the final speed of our acceleration. So take another moment to pause and think what equation we should use to find Vx. Here we want to avoid using the acceleration because this is a rounded value. So if we avoid the acceleration, we have an equation that doesn't have acceleration in it. We can plug in the values that we know, and we can find the final velocity at the end of the segment, which will be our velocity during the whole rest of the segment. If we are rounding to sig figs, we're going to say that the velocity here is 15 meters per second, but as long as we're continuing to do calculations, we're going to continue using this value and just round our final values here for parts A and B, round these to the appropriate number of sig figs. The third thing we're asked is, what is the 40 time? The 40 time is the total time it takes to do that 40-meter dash. This total time is going to be the time that it takes for the acceleration phase and also the time for this cruising phase or this uniform motion phase. We know the time here is 1.7 seconds. We don't know the time in this portion here. But this is uniform motion. When we have uniform motion, there's only one equation for us to use. It's very similar to constant acceleration, but there are only 3 variables for us to consider. And the equation is basically displacement is velocity times time. This equation here is what you get if you plug in 0 for any of your constant acceleration equations, because uniform motion is a constant velocity motion, which also means that the acceleration equals 0. In this case, we know that the velocity during this segment is 15.29 meters per second. We're going to use the full value and round later. We also said that the displacement during this interval would be 27 meters. If he does 13 meters during the first part and he's doing 40 meters total, this would have to be 27 meters there. And so we can use our equation here to figure out how much time it's going to take for our player to finish this race. And we found the time for this second portion of the race. The total time will be the sum of the time for the first part and the time for the second part. We can add those two together and find his total 40 time. As you can see, this is an exceptional, I dare say unrealistic 40 time for this player. Now that we have all of these different answers that we've been, to these questions we've been asked, we can find the position, velocity, and acceleration graphs. In this case, we want to tabulate what we have. We know that at t equals 0, our position was 0. We're starting at the origin. We know that our velocity was 0 because we're starting from rest, and our acceleration during that interval we found to be 9 meters per second squared. At t equals 1.7 seconds, we found that we were at the 13 meter mark. Our velocity had reached 15 meters per second. And our acceleration at this point goes to 0 because we had uniform motion. And then for the second half of the race, going all the way out to 3.4 seconds, the total length of the race, we end up at the 40 meter mark at the end of the race. We maintain this constant speed the whole way, and our acceleration is 0 for that whole time. So we can go ahead and sketch these graphs. We need our time, our horizontal axis, to go from 0 to 3.4, and we need our position to go from 0 to 40. We need our velocity to go from 0 to 15, and our acceleration to go from 9 to 0. So in this case, we have a constant acceleration of 9 meters per second squared during this first interval, this first 1.7 seconds. So our acceleration is 9 during that region, and then it's 0 for the rest of the race. Our velocity here starts at 0, and it reaches 15 meters per second at 1.7 seconds. So we can reach 15 right around there. And again, if we know we have constant acceleration, we have a horizontal graph here for a constant acceleration. Constant acceleration means a linear velocity. So our velocity should be a straight line there. Here, our acceleration is 0, so our velocity is constant. And if our velocity is constant, that means that we have a horizontal line here representing the velocity. And then finally, with our position, we know our position at t equals 0 is 0. We know that at 1.7 seconds, we're at about 13. And then we know that at about 3.5 seconds, we are at a position of 40 meters. In this portion here, we have 0 acceleration, constant velocity, and so a constant velocity will give us a linear position, a linear change in position in the second portion here. So this is definitely going to be a straight line. In this portion here, we have a constant acceleration, means we have a linear velocity and a parabolic acceleration. A parabolic acceleration that is concave up because we have a positive acceleration. We know that we have to have a continuous and smooth transition, so we have to keep the slope here the same. Our velocity at the very beginning is 0, so we need to have a slope of 0 here at the beginning, and so we'll have a concave parabola that will connect these 2 points and will meet these curves that we need them to have. Something like that. And so we have our acceleration, velocity, and position graphs for this player.